Okay, so this is the first installment of a series of notes that I plan to post so that you guys can go through a set of notes that we'll reference in class and also give you a chance to review some of the theory as we go through more examples in class time. So this starts out with an introduction to a finite element course. We'll review the syllabus and expectations in class. So let me go ahead and jump into what I mean by the finite element method, what we use it for. So we're using a commercial software package called COMSOL. Allows you to do multi-physics, such as if you have chemicals in the environment and you want to understand how those chemicals will absorb into a structure and perhaps lead to deformation. There's other things that you can do with these. The software package allows you to look at the internal structure. Say you have a flux of these chemicals as these points here. Maybe this is water molecules. They interact with, let's say this could be a liquid crystal attached to a polymer backbone. So we want to know, how do we understand this, and what are the most critical material physics? In this case, it's diffusion absorption of chemical species and elasticity. So given that, we want to use things such as a finite element model to be able to look at different geometries, different types of constituent behaviors. I'll get into what I mean by that in a few moments. But basically understanding, how does chemistry give rise to a shape change in this case. So coming back to the original idea of this concept of what is finite element analysis. And it was first proposed by Hrendikov in 1941, called the framework method, and applied to solids and solid bars and beams. Later on, Courant discussed what's called a variational form and introduced something called interpolation functions. We'll get into these in much greater depth later. Basically what interpolation function does is what you're familiar with in terms of interpolating from one point, let's say right here, to another point. You want to know, what is the stress across this line, what are the displacements or strains across this line. These interpolation functions will allow you to do that. So then you will only get solutions at discrete points, and then we'll interpolate in between them. So what you'll find is the more points you have, the larger the memory you need on a computer, because you have to store information at each point. For example, if it's a 2D mechanics problem, you have to store displacements in two directions, at this point, and this point. So in terms of degrees of freedom, you have 2 degrees of freedom per node, 6 degrees of freedom per element for a triangular element. Conceptually, what I mean in terms of a finite element problem is, imagine you have an elastic body, and perhaps this solid mechanics body responds to light, maybe heat, and chemicals. These will diffuse into the material. You may also apply traction. So this is an external load over an area, but applied on the surface. So you can imagine this is a force per area that'll generate internal stresses. You may also have internal electric fields, concentration due to these effects. And then down here I'm constraining it. Alright, so what we do is we do something called a discretization. So instead of getting a continuous solution everywhere, we break this problem into smaller pieces. So these are your finite elements, all these triangles. It turns out that then we can apply simpler equations at each one of these elements, and then we have certain algorithms that allow us to glue these back together. And once they're glued together, we can put boundary conditions on the surface and interpolate what happens inside based on certain balance laws like Newton's law or Fourier's equation.